Here is a classic Oxford admissions problem. Take a unit square. Inside it, draw a tilted rectangle so that each vertex of the rectangle touches a different side of the square. At every corner of the square, the rectangle creates a 45-45-90 triangle. The short side of the rectangle has length x. Along the bottom side, x plus x prime equals 1, since the full side is 1. The question is, what is x? We already have a beautiful synthetic proof of this problem that uses no algebra at all, just pure geometric construction. If you haven't seen it, the link is in the description. But today, we take a completely different approach. We want to appreciate the power of algebra and analytic geometry. We will use two different methods, each starting from the same corner triangle, but extracting a different equation. Both arrive at the same answer. Let's see how. Proof 1 takes the most direct route. Look at the small corner triangle at vertex A. It has two equal legs, each of length x prime, and its hypotenuse is the short side of the rectangle, which is x. In any 45-45 minus 90 triangle, the hypotenuse is root 2 times each leg. So immediately we can write x equals root 2 times x prime. That is the key geometric insight for proof 1. Now we use the unit side split. Since x plus x prime equals 1, x prime is just 1 minus x. Substitute that into our equation. We get x equals root 2 times the quantity 1 minus x. And notice something important. After this single substitution, the geometry is completely gone. Everything from here is pure algebra. Distribute root 2 on the right side. We get x equals root 2 minus root 2 times x. Now move the root 2x term to the left. Factor out x, that gives us x times the quantity 1 plus root 2 equals root 2. Finally, divide both sides by 1 plus root 2. X equals root 2 over 1 plus root 2. Almost there, but this fraction has a radical in the denominator. To clean up the denominator, we rationalize. Multiply top and bottom by the conjugate, 1 minus root 2. The denominator becomes 1 plus root 2 times 1 minus root 2. By the difference of squares, that is 1 squared minus root 2 squared, which is 1 minus 2, which is negative 1. The numerator is root 2 times 1 minus root 2, which expands to root 2 minus 2. Dividing by negative 1 flips the sign. And we arrive at x equals 2 minus root 2. That is roughly 0.586. Proof 1 is complete. Now let's try proof 2. We start from the exact same corner triangle at vertex A. Same legs of length x prime, same hypotenuse x. But this time, instead of the side ratio, we use the Pythagorean theorem. X squared equals x prime squared plus x prime squared, which simplifies to 2x prime squared. Notice the difference. Proof 1 gave us a linear equation, but this squaring is about to send us into a quadratic. Again, substitute x prime equals 1 minus x. Now expand the binomial. 1 minus x, quantity squared, is 1 minus 2x plus x squared. Multiply through by 2. We get x squared equals 2 minus 4x plus 2x squared. Rearranging. Move everything to one side. X squared minus 4x plus 2 equals 0. A clean quadratic. Apply the quadratic formula. A is 1. B is negative 4. C is 2. The discriminant is b squared minus 4ac, which is 16 minus 8, which is 8. Root 8 simplifies to 2 root 2. So x equals 4 plus or minus 2 root 2, all divided by 2. That simplifies to 2 plus or minus root 2. We have two roots. Now comes the physical reasoning. X is a length along the side of a unit square. It has to be between 0 and 1. 2 plus root 2 is about 3.41, far too large. We reject it. The valid root is 2 minus root 2, approximately 0.586, exactly the same answer as proof 1. Both algebraic roads lead to the same place. Let's take a step back and review the 7 facts that powered both of these proofs. Fact 1. The unit side split. x plus x prime equals 1. This is the shared starting point for both proofs. It lets us eliminate x prime and work with a single unknown. Fact 2. The 45-45-90 triangle. The hypotenuse is root 2 times each leg. This is proof 1's key geometric observation. It gives a direct linear relationship between x and x prime, which is why proof 1 never encounters a quadratic. Fact 3. The conjugate product. A plus b times a minus b equals a squared minus b squared. When proof 1 arrives at root 2 over 1 plus root 2, multiplying by the conjugate turns the denominator into 1 minus 2, which is negative 1. This is how the radical disappears from the answer. Fact 4. The Pythagorean theorem. C squared equals a squared plus b squared. Proof 2 uses this on the same corner triangle. Since both legs are x prime, we get x squared equals 2x prime squared. The squaring is what produces the quadratic equation. Fact 5. Binomial expansion. 1 minus x squared equals 1 minus 2x plus x squared. After substitution, this generates the quadratic x squared minus 4x plus 2 equals 0. Fact 6. The quadratic formula. With a equals 1, b equals negative 4, c equals 2, the discriminant is 16 minus 8, which is 8. Root 8 is 2 root 2. The two roots are 2 plus or minus root 2. Fact 7. The physical constraint. X must be between 0 and 1, since it's a segment inside the unit square. 2 plus root 2 is about 3.41, way too large. We reject it and keep x equals 2 minus root 2. Both proofs arrive at this same value. So both proofs agree. X equals 2 minus root 2, approximately 0.586. Now I want to point out something deeper about what just happened. In both methods, algebra abstracted us away from the geometry very early on. After just one or two geometric observations, the picture disappeared and the rest of the work was entirely symbolic. Distribute, collect terms, apply a formula. This is extremely efficient. The heavy lifting is localized. You don't need to hold the whole picture in your head. And this is the fundamental reason why most mathematics textbooks look like pages and pages of algebraic derivation. Algebra lets you compute without seeing. But here is the other side of that coin. For a geometry problem, a solution that loses contact with the geometry is never quite fully satisfying. You get the answer, but you don't see why the answer has to be what it is. That is exactly why the synthetic proof of this problem exists. No algebra, no formulas, just construction and proportion. The geometry speaks for itself. We will revisit this tension between geometry and analysis many times in future problems on this channel. For the pure geometric route to this answer, check the other video linked in the description. Thanks for watching.